There was a couple of questions I skipped. One of them was this one. And so I want to do a couple of examples. First of all, I want to do this one to help illustrate Faraday's law. So you have two light bulbs in a magnetic field. And the magnetic field is increasing into the board or into the screen, however you want to say it. And as a result, if the magnetic field is changing rapidly enough, both light bulbs will go on. Okay, and this field is due to a solenoid. What happens if I take a wire and connect it between points P and Q as shown in the figure? Do the two light bulbs stay on? Do they both go off? Or does one of them go off? That's the question. Unfortunately, I'm not able to demonstrate this. I'm not sure I understand. I'm not moving, the light bulbs aren't fixed, it's just the magnetic field is increasing. Let's say it's increasing linearly with time. The bulbs aren't moving. The bulbs are just sitting there. So I have a time-varying flux through that loop, and the light bulbs go on. The two light bulbs go on. But the question is, if I put a wire between points P and Q, then what happens? So let me draw a picture. So somehow we're making the magnetic field increase into the board. I have two light bulbs. They're not the greatest light bulbs. And then, so these are lit, and then I take a wire, and I just connect them between these 2 points. So what happens? Yeah, the extra wires are short. Right? Really, I'm shorting. It's a short here. So what happens? Does this go off? Do they both go off? Stay the same? So let's take a look at this equation. Remember, this is the flux, the time rate of change of the flux enclosed by the loop. So in order to analyze this, first of all, how many loops are there in that picture? How many loops do you see? 3. So we got to consider all 3 loops. Suppose I look at this loop. What is this in that loop? It's 0. There's no changing magnetic field within the area enclosed by the loop. Okay? So there's no changing flux. That kind of says that, oh wait, is this not going to go on? Well, it does tell you that, right? Because there's no changing flux in here. This is not going to go on. Now, are they both off or what? Well, I have 2 other loops. I have the big loop that goes all the way around. and I have my original loop, this loop. Now, in both loops, the flux is changing. Yeah, I'm changing the current in the magnet that's producing the field, if that's what you're trying to ask. Yeah, there's a magnetic field there's a magnetic field here, and there's a magnetic field enclosed by this loop. Both these green loops that I've drawn enclose a magnetic field that's changing. Both of them. This one does not. So if both of them have a changing magnetic field, then this says that there should be current going through either this loop or this loop. You mean this one? Why isn't there a magnetic field here? Yeah, the source isn't over here. It's over here. Yeah, there's no magnetic field here. Right, this is a solenoid. The solenoid produces a uniform magnetic field straight into the board. Outside the solenoid, the field's zero. So there's no way there's no magnetic field here. Right? That's how we define a solenoid. Solenoid, an ideal solenoid, the magnetic field, and it doesn't have to be ideal really, but the magnetic field is all in here. There's nothing out here. So you're on the left here. There's no magnetic field. There's no changing flux. No, it's a solenoid. It's a solenoid, sorry. So we have two loops. This one, this big green one, and then the one inside. It really goes around the red one, the two bulbs. Both of them, maybe I'll not draw this one because that one's confusing. So the red loop and the green loop, they both have a magnetic field inside the loop. So that means you can have current going this way. However, there's a wire here that shorts this out. And current likes taking the path of least resistance. So if current likes taking the path of least resistance, the electrons are going to go like this. Okay, they're gonna go, I'll use blue. They're gonna take this path. So the one on the right will stay on. The one on the left will go out. Normally I do a demo similar to that in class, but I don't have that demo. But Tyler created a video for us of a similar demo, not like this. So let me show that to you. I told you guys a lot of demos in this class, in this topic. So let me switch. I got to go to YouTube because he created a video into YouTube. And, oops, this thing's starting already. Okay, so this is a video that Tyler created for us. So here you have basically a coil producing a magnetic field. The power supply for the magnetic field is on the right. And you basically have a loop here, a circular loop. We have this blue device here, this blue basically junction box that you can connect resistors, and then you have another blue one on the right. And then you have this coil, basically a wire that we're going to change the area. I'll let him tell you about the
Here's a quite interesting demo to take a look at today. And this is consideration of how magnetic fields can affect a circuit. Here is a Pasco multimeter, in which we're measuring the voltage induced across. Follow the circuit with me. Directly back in. And in between, we have a 250 turn labeled coil with an iron core attached to a variac. So as I turn on the variac, we can see the magnetic field here is inducing a voltage. But we move the wire behind now, we can take out most of that magnetic field and reduce the voltage on it. And back. And forward.
Yes, if I flip the bulb to the other side, the other bulb would stay on. That's correct. Oops. Let me close that. Yeah, that idea of the area enclosed by the loop is very important, and being able to understand this. Yeah, it's induction, right? I mean, that's what that works on. So what if the loop was a straight wire, like you thought before? That would be different. If it was a straight wire, then you would still have a magnetic field in the loop we were talking about. But then, if this was a wire, the magnetic field would be stronger here than here. Right, so the field would be weaker here, so you would still have this loop have you still have the loop having an enclosing a magnetic field, but it would be smaller. All right, so if this was a wire that was centered over the whole thing, the magnetic field would be strongest here and weaker here. You might not see the effect. You might see this get a little dimmer, but you might not see it go off. Does that make sense? Yes, no. Did I answer your question? Okay, I hope I did. I'm not getting a response, so. The other problem I skipped was kind of an important problem. And so I want to go through that now. It was this one. Consider, again, we're going to consider solenoid. Okay. Oh, I got enough. So I have one more question here. What if we had the loop go through the solenoid? So the loop, the entire loop was inside the solenoid, you're saying? So you're saying the loop is perpendicular to the magnetic field? Then if it's perpendicular to the magnetic field, then you don't have any flux, right? Yeah, all you'd be doing is shorting the loop. Nothing would be on anyway, because you're perpendicular to the magnetic field. Well, if you're perpendicular to the magnetic field, none of them will be on, with or without that extra wire. Oh, but only if the shorting wire was perpendicular. I see. So I took this wire and put it up here. There won't be any changing flux in that loop. All right? Well, Patrick said if I took this blue wire and it wasn't blue, it's purple. I took this and I lifted it up right over here. So it's sticking out of the plane, perpendicular to the magnetic field. What would happen? The bulbs will probably just stay on still because that thing's not doing anything. There's no source. There's no source of current, right? Because the magnetic field is perpendicular to the loop if I do that, and so there's no source. I mean, that's a good question. Right, but if I take a loop, I'll do this with a wire, I guess. Let me find a wire. If I do this, and this thing sticks out perpendicular to the magnetic field, there's no field lines going through it. Isn't that true? Yeah, it is conductive. But there's no magnetic field going through this. It's hard for me to hold it up, but there's no magnetic field going through this loop. There's no source. Okay, so the next problem I want to do is this. We have a solenoid with a time-dependent current. I want to know something about the induced EMF in a loop of wire that's inside the solenoid. Suppose I have a big solenoid and I just put a loop of wire in the solenoid. For example, let me go grab my loop of wire. Maybe a loop of wire like this, and I put it in a solenoid. What's the induced EMF in that loop? What's the induced field? So let me draw a solenoid. Obviously, I'm not drawing the coils real tight, but I can't do that for a drawing, so. All right. So let's assume that the current in the solenoid is like this. So the magnetic field inside points that to the right. Patrick, let me answer your question later. I'm sorry, I need to continue. I'll get to your question later. Okay. So suppose we have a magnetic field that points to the right because of the current flow. Okay. I want to know the induced EMF. So B is mu naught N times I. Okay, we're assuming an ideal solenoid. And I want to look at what happens to a loop. Let me draw a loop inside. We're going to place a loop of radius r inside the solenoid, and the plane of the loop is perpendicular to the magnetic field. Okay. Which means that the normal to the loop is either parallel or anti-parallel to the magnetic field. Okay, so what I want to look at is this expression. And I want to get the electric field out of this. I want to determine the electric field. I can determine the induced EMF by just taking the derivative, right? This is just delta V. And that's going to be easy because what is this equal to? Well, so how do I choose the normal to the loop? Well, I got to determine it by how I'm going to integrate this. I want to be consistent with how I'm going to do this integration. Okay? So, I'm going to use the right-hand rule. I'm going to choose my normal in that direction, but then when I integrate E dot dl, I'm going to integrate in the same direction. So I'm going to integrate this way. Basically, it's the same direction as the current. To integrate that, if I integrate in that direction, I use the right-hand rule, the normal point's perpendicular to the plane of the loop. I'm going to integrate in the same direction. Okay. So then I'm going to make this dot product positive. And so I'm going to get minus the integral of b, which is mu naught ni, times pi, times dA, sorry. Since this is constant, so that's what the flux is, and then sorry. I kept messing up, sorry. Okay, sorry about that. So then I'm going to take the derivative of this, and I forgot my derivative again. That's the induced voltage. This integral, why did I make it negative? I'm just calculating minus d phi dt, right? I forgot the derivative symbol, sorry. What happened after that? Okay, so I'll start again. I'm calculating this. So I copied it over here. This is the negative of the time rate of change of flux. That's why I have the minus sign there. So I copied the minus sign here. And I kept it here. I just forgot the d by dt's. I just kept forgetting to write them. That's all. Does that answer your question? Right? I started with the time rate of change of flux. I wrote the expression for the time rate of change of flux here. And then I copied it down here where I actually put in the value for the magnetic field. And then here I had forgotten to put it in, and then I added it in afterwards, and I apologize for that. Yeah, remember what I said was I chose the magnetic field in the same direction as the normal to the loop, so that when I take the dot product, right, when I have the dot product of two vectors that are parallel to each other, right, if I take the dot product of two vectors that are parallel to each other, the unit vectors that are parallel to each other, I just get one, right? So if I have, and I am skipping steps, but if I wrote the magnetic field like this, and then the normal to the surface like that, don't I just get 1 when I take the dot product of those two I-hats? And they go away because it's a dot product. Okay, that's what I did. I did it quickly because, I mean, that's what I've been doing. Okay. When the two vectors are parallel to each other, or when they're parallel to each other, I either get 1, or if they're anti-parallel, I'll get -1. Okay. So here's delta V induced. Well, what I want to do is calculate the electric field from this. This is equal to the integral of V dot dl. The magnetic field is constant. Okay. The magnetic field is constant. As I go further and further, and so really what's going to happen is, since the induced EMF depends on R, the electric field will depend on R. This field has cylindrical symmetry. Correct. The R is the radius of the loop of the wire, right there. This field is going to have cylindrical symmetry. It's going to have the same value for any value of R. So this integral is going to be easy. I integrate my electric field around this loop. And so I can solve this for the electric field. That is the electric field. How do I know that the electric field is positive or negative? Well, I chose to integrate in such a way that I use the normal to the loop. I use the right-hand rule. The minus sign will come out from over here. I assumed a direction for the electric field, and I integrated in a particular direction. And if I was wrong, then the minus sign will tell me I was wrong. Just like when I do Kirchhoff's laws, right? Oh, yes. Just like when I do Kirchhoff's laws. Well, I have a loop. So I have a loop. I said that the field is going to have symmetric symmetry because V depends on R. That means it's going to have the same value for any R. If it has the same value for any R and I integrate around a loop, then my integral is going to end up being 2 pi R. I can pull the E out of the integral. And all I'm going to have is the circumference of the loop. Right? If E depends on R, if V depends on R, then for the same value of R, the field will be the same. The system has cylindrical symmetry. Means I can pull the E out, and if I'm integrating in a circle, I got to get 2 pi R. Does that make sense? Did I drop it? Sorry. Okay. We okay so far? Okay, well, I'm going to continue then. How did I know? Oh, well, the radius doesn't change, right? What is the only thing that changes? What's the only thing that's time dependent here? This is not time dependent, that's not time dependent, that's not time dependent, that's not time dependent. So when I take the derivative, I know the only thing that depends on time is the current. Does that make sense? Or did I answer your question? Okay. So E is, this is the induced E. Has a minus sign, it's minus di dt, it depends on minus di dt. If the current is positive, is increasing, if the current is increasing, the electric field that's induced is opposite to the increase in current. Okay? If di dt is less than 0, then the induced EMF is in the same direction as the current. So if di dt is bigger than 0, the current is actually, the electric field is this way. If di dt is less than 0, then you have the electric field in this direction. So I chose to integrate this way because I was saying the electric field was this way. I chose this so this was positive. But I got a minus sign. It just tells, the minus sign just tells me I chose incorrectly, just like when you do assign currents in Kirchhoff's laws. What is the direction of the electric field? The electric field is either clockwise or counterclockwise as you look towards the solenoid. If I look from the front, it's either clockwise or counterclockwise. So in this particular case, it's opposite the direction of this current. So if di dt is bigger than 0, the electric field is going to circulate this way. The electric field circulates in this case. They form closed loops because this is not a conservative field. If we put a charge inside the solenoid, guess what would happen? If I just put a stationary charge inside the solenoid, what would happen? It would experience a force because of that induced electric field. And that force would cause the charge to go in a circle. This electric field requires no charges to create it, and it's mathematically, you say it's divergenceless, just like a magnetic field. The field lines form closed loops. Correct. What you said, Morgan, is correct. The charge would only go in a circle if the current in the solenoid was changing. That is correct. That's what we're assuming here. How big would the circle be? We'd have to calculate it. I mean, you have to use Q times E equals mv squared over R. It just depends on the induced field. So this induced EMF, induced electric field, requires a time-varying magnetic field, but no physical circuit is required for that to exist. If you put a wire inside the solenoid, it would cause the electrons to move along in a circle. All right, that's how you get the induced EMF and voltage. So one of the things about this induced voltage is that it's not related to a potential energy because this comes from a non-conservative force. We cannot say this. Oh, let me rewrite this, sorry. We cannot say this. That's not true. This only comes from, this is only true if the electric field is conservative. If the electric field is not conservative, we cannot say this. It turns out that there's another, if you throw in another term here, then you can put an equal sign there. But we're not going to deal with that here. You can't define a potential energy for this. Okay? You can't define a potential energy for this. And you can't relate the electric field to the gradient of V. There actually has to be another term there, it turns out. So I want to do another example of induced EMF. But this is arising from moving circuits. So this is a force, this is a wire in a magnetic field that's moving. Or a rod, let's just say a rod in a magnetic field that's moving. So let me draw my rails. So here's some rails. Okay. Here's a rod of length L. And let's say we gave it some initial velocity V rod. Okay, this is the initial velocity of the rod, V rod. We have a magnetic field that points into the board. Okay? What happens? Okay? Let me blow up this picture. So, according to the Lorenz Law, there's going to be forces on these charges. That rod, let's assume that rod's a conductor. Let's assume that the rails are made out of conducting material. Let's assume there's no friction in the on the rails, or no friction between the rails and that conducting rod. If you use Lorenz Law, there's going to be a force on the electrons. And if you use the right-hand rule, you will find that the magnetic force on the electrons is downward. So the electrons will move downward, leaving positive charge at the top of the rod. And these charges will accelerate until the electric field produced by the separation of charges, or the force due to the electric field due to the separation of charges, is equal to the force due to the magnetic field. In other words, QVB will end up being equal to QE, where E is the result of the separation of charges in the rod. And in this particular case, with the rod moving to the right, the magnetic field pointing into the board, the current is going to be upward. In other words, you're going to get a counterclockwise current because the electrons are going to go through the rails too. So you will get a counterclockwise current in this particular case. And so since QE ends up being equal to QVB, where the E ends up being the electric field due to the motion of the rod, then we can say that and so E motional, I guess not a good term, but is V times B. But if the magnetic field is constant, or let me rephrase that. If the magnetic field is uniform, then the electric field will be uniform. And so the electric field is easily related to a delta V. This is just going to be equal to delta V motional over L. And I'm just working with the magnitudes, okay? That's why there's no minus sign in there. If you're questioning whether or not there's a minus sign, I'm just looking at the magnitudes. And so we have E motional is V times B, and delta V motional is V times B times L. V is V of the rod. That's called motional EMF. If there were a resistance, right, there's always a resistance, then there's going to be a current that's produced. It's going to be equal to delta V motional over R. So, what do you think is going to happen to the rod as it's producing electrical energy? What happens to the rod because of the electrical energy that's being produced as a result of the fact that it's moving? What do you think happens to the rod? I have electrical energy in the circuit. Where does it come from? Well, it comes from the kinetic energy of the rod. So what's going to happen is the rod's going to want to slow down. I'm converting kinetic energy into electrical energy in this particular case. And so the rod will slow down. And that makes sense, because if you look at it, if the current that's induced is this way, which I showed a couple slides ago, I have a magnetic field into the board, a current I upward, the force is going to be that way. So there's going to be a resistive force that's going to slow this down. So this produces okay? That's going to produce a resistive force to slow down the rod. So the kinetic energy is being converted to electrical energy, and that's being dissipated by the resistance of the circuit. Why can't the current be the other way? I can answer the question regarding what should the direction of the current be by considering conservation of energy. Okay, if I didn't go through the couple slides that I did a few minutes ago with the separation of charge, I can still deduce that the current has to be this way by the following argument. What if the current was downward? If the current was downward, then the force on the rod would be to the right and the rod would speed up. Why can't that happen? Or we would like it to happen, but why can't it happen? It won't happen because of the fact that energy has to be conserved. If the current was downward, then the force on the rod would be to the right. The rod would speed up forever. You're getting something out without putting anything in. You would violate the law of conservation of energy. So the force on this rod is to the right. In fact, we can calculate the force. We can calculate the force a number of ways. So let's assume that L is 1.6 meters. B is 0.8 Tesla. And V is 5 meters per second. Okay, so if we find delta V is going to be $5 meters per second. I'm just going to finish this slide and then I'll be done. The length of the rod. And then this ends up being 6.4 volts. The current, well, I need to know the resistance. If I want to know the current, I need to know the resistance. So let's say the resistance was 96 ohms. So that means I is going to be 6.4 volts over 96 ohms. And that comes out to be 0.067 amps. So the power ends up being 0.43 watts. Every minute you use up 26 joules. So how do I find the force? Well, the force is just going to be obtained from ILB. .067 amps, 1.6 meters, 0.8 Tesla, and that gives you 0.086 newtons. Okay. We can also calculate it from the fact that power is force times velocity. You take the power of 0.43 watts and divide it by the velocity of 5 meters per second, and you will still get the 0.086 newtons. So I need to stop here because I have another class after this. You guys okay? You guys had a lot of questions. I'll try, Patrick, to answer your question. I just didn't want to. I just wanted to keep moving. So I'll ask. I'll answer your question next time, Patrick. Okay. All right. Take care, everybody.